transitions between two states and use your matrix model to predict both future and past states. We'll be focusing on Objective 4.14 from AP Precalculus. This means we'll construct models based on percent changes, use matrix multiplication to find future states, and even find past states using matrix inverses. These skills, like constructing models and applying numerical results, are essential for success in AP Precalculus and beyond. Let's get started with our first example. Imagine a country with two main cities, City A and City B. We want to model how the population might shift between these two cities each year. Let's say a certain percentage of people stay in City A each year, and the rest move to City B. Similarly, a percentage of people in City B stay there, and the rest move to City A. This is a classic two-state system. The first step, Objective 4.14a, is to construct a model for this. We'll start with the transition rates. Let's say 90% of people in City A remain in City A, and the other 10% move to City B. This means that after 1 year, the new population in City A will include 90% of the old population from A. Let's also say 80% of people in City B remain in City B, and the other 20% move to City A. So, the new population in City A will also include 20% of the old population from B. The new population in B will include 80% of the old population from B and 10% of the old population from A. Now, let's turn these percentages into a transition matrix, which we'll call T. This matrix will help us model the change from 1 year to the next. A transition matrix T is a square matrix where the entry in row I, column J, represents the probability or percentage of moving from state J to state I. It's important to remember that from states are columns and to states are rows. Let's build our matrix T based on our population shifts. The column for City A represents the population coming from City A. Of that population, 90% goes to City A, row 1, and 10% goes to City B. The column for City B represents the population coming from City B. Of that population, 20% goes to City A, row 1, and 80% goes to City B, row 2. And there is our transition matrix, T. Notice that the sum of the entries in each column is 1. This must always be true for a transition matrix, because everyone has to go somewhere. The population from City A, 0.9 plus 0.1, is fully accounted for, and so is the population from City B, 0.2 plus 0.8. We have a model of the transitions, but we also need a starting point to make predictions. This is called the initial state vector, and we'll label it as x sub 0. A state vector is a column matrix that lists the number or percentage of people in each state at a specific time. We'll use fractions of the total population for simplicity. Let's assume that initially, 30% of the total population is in City A and 70% is in City B. So, our initial state vector is x sub 0 equals the column vector 0.3, 0.7. This vector tells us the distribution of the population between the two cities at the start. So, the objectives are met for constructing the model. The question is, how does it help us? Now for Objective 4.14. B. Applying the model to predict future states. To find the population distribution in the next year, which we'll call x1, we multiply the transition matrix T by the initial state vector x0. The formula is simple. The next state, x1, equals the transition matrix T times the current state, x0. The product of the matrix T and the vector x-0 will give us a new state vector that represents the population distribution after one transition period. Let's plug in our values. x1 equals our transition matrix T times our initial state vector x0. Remember how to multiply a matrix by a vector? We take the dot product of each row of the matrix with the vector. For the first row, we get 0.9 times 0.3 plus 0.2 times 0.7. For the second row, we get 0.1 times 0.3 plus 0.8 times 0.7. This simplifies to 0.27 plus 0.14 for the first entry, and 0.03 plus 0.56 for the second. Calculating these, we find that x1 equals 0.41, 0.59. This new state vector, x1, tells us that after 1 year, 41% of the population will be in City A and 59% will be in City B. So you can see the population distribution has shifted towards City A. What if we want to look further into the future? We can find the state after 2 years, x sub 2, by applying the same process to our new state vector, x sub 1. So, x sub 2 is t times x sub 1. We are repeatedly multiplying the transition matrix by the state vector to predict further into the future. This process can be repeated for any number of steps, n, using the formula x sub n equals t to the n times x sub 0. Let's calculate x sub 2. We multiply our transition matrix by the state vector we just found. Again, we perform the matrix multiplication. We get 0.9 times 0.4, 1 plus 0.2 times 0.59 for the first entry, and 0.1 times 0.4, 1 plus 0.8 times 0.59 for the second. This simplifies to 0.369 plus 0.118 and 0.041 plus 0.472. The result is x sub 2 equals 0.487, 0.513. After 2 years, 48.7% of the population is in City A and 51.3% is in City B. You can see the distribution is continuing to shift towards City A. This repeated multiplication allows us to predict the future population distribution over any number of years. This repeated process brings us to a fascinating concept, the steady state. The steady state is a distribution where the system stops changing from one step to the next. The population distribution will no longer shift year after year. We find the steady state, x sub s, by repeatedly applying the transition matrix T. After many iterations, the state vector x sub n will converge to the steady state vector. We can find this steady state more elegantly. The definition of the steady state is that applying the transition matrix T doesn't change it. So, T times x sub s must equal x sub s. We need to solve this. First, we rewrite x sub s as I times x sub s, where I is the identity matrix. Subtracting T times x sub s from both sides gives us the equation for finding the steady state. To solve this, we set up a system of equations from the matrix I minus T. For our matrix, I minus T is this matrix right here. The system of equations is negative 0, 0.1, x sub 1, plus 0.2 x2 equals 0, and 0.1 x1 minus 0.2 x2 equals 0. These are the same equation, just opposite signs. So we have one equation, 0.1 times x1 equals 0.2 times x2, which simplifies to x1 equals 2x2. The steady state is when the population of City A is double that of City B. Because the state vector must sum to 1, this means 1/3 of the population is in City B and 2/3 is in City A. So far, we focused on moving forward in time. But what if we want to know what the population distribution was in a previous year? We can use the inverse of the transition matrix, T inverse, for this. Just as we used T to go from the past to the future, we use T inverse to go from the future to the past. The formula is x0 equals T inverse times x1. We must first find the inverse of our transition matrix T. Our matrix T is this. We'll use the 2 by 2 inverse formula, which is 1 over the determinant, times the adjusted matrix. The determinant of T is 0.9 times 0.8 minus 0.2 times 0.1, which equals 0.7. The adjusted matrix is found by swapping the main diagonal entries and negating the off-diagonal entries. So, T inverse is 1 over 0.7, or 10/7, times this matrix. Now let's verify our earlier work. We know x1 was 0.41, 0.59, and x0 was 0.3, 0.7. Let's use T inverse to go from x1 back to x0. We multiply our T inverse by the state vector x1. The result of the multiplication is 10/7 times the vector 0.21, 0.49. When we distribute the 10/7, we get 2.1 over 7, 4.9 over 7, which simplifies to our original state vector 0.3, 0.7. It works! We successfully predicted a past state using the inverse matrix. Let's quickly recap what we've learned. First, we learned how to construct a transition matrix from a two-state scenario involving percent changes. Remember, the columns are from states and the rows are to states. Next, we used our model to predict future states. We found that the next state, x_n plus 1, is the transition matrix T times the current state x1n. We also learned about the steady state, the stable long-term distribution. We found it by solving the equation it times the steady-state vector equals 0. Finally, we explored how to predict past states using the inverse matrix. The past state x_n, one is the inverse matrix T inverse times the current state x_n. You are now equipped to model scenarios involving transitions between states and use these matrix models to make predictions about the future and the past. This is a fundamental concept in fields like economics, sociology, and even computer science. Great work!